If we start with a situation, say a particle at a point in space and time, there are two ways in which we can ask what will happen next. We can ask, given we know the forces on the particle and the particle's initial position and velocity, where the particle will be after an amount of time has passed, and we can get an answer using Newtonian mechanics. Or if we instead know the particle's initial position, its final position, and any constraints on the motion, we can ask what trajectory is the one that we will observe happening in nature. We can think of many different possible trajectories. This second approach still gives us the equations of motion that obey Newton's equations. The starting point is the principle of stationary action, also known as the principle of least action. There is a mathematical object called the Lagrangian, which contains information about the entire system. In simple systems, the Lagrangian is equal to the kinetic energy minus the potential energy. In more complicated systems, the Lagrangian is just a function of the spatial coordinates and their derivatives. Now, I mentioned this is the principle of stationary action, so let's define the action. The action, S, is the integral from one time t0 to a later time t1 of the Lagrangian over a trajectory with respect to time. The principle of stationary action tells us that when an infinitesimal change in the action is equal to 0, and so we say that the action is stationary or minimised, that is the trajectory that happens in nature. We'll now turn our attention to quantum mechanics. Feynman's path integral formulation is a quantum mechanical version of the principle of stationary action. This formulation is based on probability amplitudes. Essentially, we want to calculate the amplitude that when a quantum particle starts at a particular point in space and time, we look at a time later and observe it at a different point in space and time. Again, we can think of many different paths that this quantum particle could take. We can even think of paths that are very different from what we'd expect classically, such as the quantum particle travelling to the moon and back. The amplitude is a complex number, whose magnitude squared is the probability for a particle to be detected at that later position. The amplitude is given by the sum of the contributions from each possible path, and is written as like so. This term here represents the contributions from each possible path that we could imagine. Each path is given equal weighting, but the phase, represented by S over h bar, is different for each one. Let's explore that. So if we draw again some potential trajectories, we'll start with the classical trajectory, and we'll represent the final phase by the direction of a short vector, as so. We'll see that paths that are close to the classical path, their vectors are in very nearly the same direction. And so we see that these paths contribute strongly in the sum for the amplitude. Whereas if we consider again these paths that deviate strongly from the classical path, and we represent their vectors, we will see that these vectors that correspond to paths that are very different to the classical path, we notice that these vectors will tend to cancel each other out. And so we are left with trajectories that are very close to the classical path.